Math 287, Cuesta College. I'm Joe Vasta, and we are covering section 8.7, variation of parameters. I have this differential equation here. It's non-homogeneous, constant coefficient, linear differential equation. And the right-hand side has a function that cannot be annihilated. So the question is, what if we cannot annihilate the driving functions? We need another method to find YP, the trial solution. And so this method, when annihilators does not work, is called variation of parameters. Let's go ahead and do a derivation. So the variation of parameters technique that we're going to do needs a derivation. And before we do the derivation of that, we need to go over something called Cramer's rule. Cramer's rule has to do with solving a system of linear equations. So we could have covered this in linear algebra. I just felt like when we were doing stuff in chapter 2 that this just would have been something that was unneeded until this moment. So you're gonna see in this derivation why we need Cramer's rule. So Cramer's rule is a rule that you can solve n by n linear systems. And we're going to look at the coefficient matrix, which is A. And we are now going to look at this thing called A1, which is gotten by writing matrix A and replacing the first column. So that's what the 1 is there. You're replacing the first column with the right-hand side vector, which is 10, 11, which you get from over here. And so A2 is the same thing. You write matrix A down and you replace the second, that's the 2, the second column with the right-hand side vector, which is this guy right here. Okay, so now what I'm going to do is I'm going to take the determinant, I'm going to take the determinant of each of those matrices there. The determinant of A is negative 14. The determinant of A1, and all I'm doing is AD minus BC. That one gives me negative 28, and the determinant of A2 is 14. So if you can do all of this, and Cramer's rule only works on square systems where you have like 2 variables and 2 equations, or 5 variables and 5 equations, it doesn't work on all systems, then you can do this. You can find x by putting determinant A1 over determinant A. And that gives me x equals 2. Y is found by going determinant A2 over determinant A. And that gives me negative 1. So my solution is 2 comma negative 1. And you can imagine that we can generalize this technique if we had 3 equations and 3 unknowns. And then we'd have A, A1, A2, A3. And so you can think of what it would look like to generalize this. We're going to need Cramer's rule for our variation of parameters, and you will not be using Cramer's rule directly in your homework. You'll just be using the recipe, the results that we get from it. So now let's get to what we want to do now, is solve a differential equation, and we'll be looking at second order linear differential equations that look like that. So when we do variation of parameters, we have to make sure that y double prime has a coefficient of 1. If it has a coefficient of x or anything else, you have to divide everything in the equation by that. So you make it have a coefficient of 1. The next step is solve the associated homogeneous differential equation and you get the complementary solution. Because it's second order, you're going to have 2 CIs, C1y1 plus C2y2. And that's my complementary solution by letting f of x equals 0. Now, the next thing we're going to do is we want to make this note that y1 and y2 solve the associated homogeneous differential equation. And I'm going to put a star there because we'll make a reference to that. So does any linear combination of those. And think back to the linear algebra, what you just found is you found the null, not the null space, the kernel of some linear transformation, and there is the linear combination of two vectors, y1 and y2. They each solve the associated homogeneous differential equation. We are free to impose two conditions when solving this differential equation. Now, if you're a math major, you're going to see more of this kind of stuff, proofs, as you take higher math classes at the university. The first condition is condition 1. We'll call it condition 1. And we're going to say that the particular solution, or the trial solution, is going to look like this. It's going to look like u1 of x times y1 plus u2 of x times y2. And we're going to assume, we're going to impose this condition that this is going to be the particular solution of our differential equation. So what we're going to do with this is we're just going to write this y sub p as u1 y1 plus u2 y2, knowing that all four of those guys right there are all functions of x. Now, this is called variation of parameters, this technique. It's because when you look at the complementary solution, we call C1 and C2 constants, and that's what most normal people call them. But those constants are sometimes called parameters. And so what we're doing is, those parameters vary over x to find the trial solution. So we are varying the parameters, and this is why this is called variation of parameters. So that is condition 1, and what we're going to do is we are going to plug y sub p into the differential equation. In order to do that, we must take the derivative of this, in fact, two derivatives of this, so we can plug it into this differential equation. Now, to take the derivative of this, you're going to have a product rule here and a product rule there. So let's go ahead and show you the results. The derivative of the first times the second plus the first times the derivative of the second, that's applied twice. Okay, the next thing I'm going to do is, well, I want to take the second derivative, and this is just going to get so outrageous. We said we had some wiggle room to impose two conditions, so my second condition is that u1 prime y1 plus u2 prime y2 equals 0. If I impose that condition, then I end up getting rid of those terms there, because you add them up, they give you 0. And now my first derivative looks like this. It looks like I'm cooking the books. I have no more wiggle room, and this will solve differential equations. So I don't have any more freedom to impose any other conditions. So I'm going to go ahead and take the next derivative, which would be yp double prime. I'm going to do two applications of the product rule. And so there they are. And I'm going to look at my original differential equation and plug y sub p into it. And so that's what it looks like. So where did this come from? This came from, this is the original differential equation with y sub p plugged in there. Now, I'm going to go ahead and it's going to get messy. Y sub p double prime happens to be those four terms, and then y sub p prime is two terms, and y sub p is two terms as well. And I got to put the a and the b in there, so it looks like that. Now what I'm going to do is I'm going to identify some terms. So this might be the most exciting part of the whole YouTube video, is when that happened. You want to see that again? Oh, it won't let me go back because I'm doing a video. Oh well, so hopefully you didn't miss that where those things jumped down. Took me forever to figure that out. Notice the ones that I circled in red, they all have y1s, or y1 prime, y1 double prime. The ones circled in blue have y2s in them. But not only do the red ones have the y1s, but they also have u1s. They all have u1s, etc. So I'm going to group the red ones first and factor out a u1 of the three red ones, and then I'm going to factor out a u2 on the three blue ones. And then that other stuff I'll put, after that. So when I rearrange things, just doing some algebra. Now, look at what we said up here. We said y1 solves the associated homogeneous differential equation, which means if I put y1 into the left-hand side, I'm going to get 0. And that's what I have here. This is going to give me 0. And same with the y2. And so I have a result there. It says u1 prime y1 prime plus u2 prime y2 prime equals f. Let's put that result there. And let's also note that now we have two things that I want to point out here. Happens to be those two equations. I've run out of PowerPoint space here, so I'm going to go to a new slide, and I'm going to put those things that I boxed in green up at the top along with the original differential equation. Okay, so I also have to remember to stay silent when it switches slides, because it will then mute me during the switching of the slides. So hopefully we didn't get cut off when I switched from slide 1 to slide 2. Okay, so here's what I have. I have our differential equation. I have the complementary solution, which is C1, has the C1 and C2. Those are the constants. And the trial solution, which has U1 and U2, which are functions of x. Then I have those things that I derived from the last page. One of them was one of my conditions that I imposed. And I'm going to notice that I can rewrite that system. This is a small system of equations. I'm going to rewrite it so it looks like this right here. Now notice, this is a linear system that has variables u1 prime and u2 prime. It's really weird because usually our variables are x and y. And it has coefficients of y1 and y2 and y1 prime and y2 prime. Those are actually the coefficients, even though they're functions of x. This is why we saved Cramer's rule until now, because we didn't really need to do Cramer's rule, but Cramer's rule works well when the coefficients are functions like we have there. So let's go ahead and do Cramer's rule. I'm going to identify matrix A, which is the coefficients on the left-hand side, y1, y2, y1 prime, y2 prime, which looks a lot like when you take the determinant, the Wronskian. Okay, so that's kind of neat. And then I'm going to identify A1 and take its determinant. A1 happens to be this matrix here, A, with the first column replaced by the right-hand side vector, which is 0, f of x. And when I take its determinant, AD minus BC gives me a negative y2f. And the determinant of A2 gives me y1f. Okay, so now I know that x is going to equal, and it's not x, my first variable is u1 prime. u1 prime is going to equal determinant A1 over determinant A. And that gives me negative y2 times f over w. And my second variable in that linear system is u2 prime. I put determinant A2 over determinant A, and that gives me y1f over Wronskian. Or, and here's the final result, this is what we were trying to get. u1 prime equals negative y2f over w, and u2 prime equals y1f over w. The procedure was very long, so we're going to memorize the formulas, the ones you see in that box there. The procedure works with variable coefficients A and B. So look at our original differential equation. We've been doing constant coefficients, but if you had variable coefficients, and we have not been trained how to solve homogeneous differential equations with variable coefficients, but we can't learn everything in this class. But this procedure works with those. And the last thing is the procedure will always yield a particular solution. So let's go to the next slide. Okay, so the next slide is the 9-step program. Oh boy, do we all need a 9-step program in these times. Well, this 9-step program is not going to help us cope with sheltering in place or not enough toilet paper, etc. This is going to help us cope with solving a second order differential equation. And let's go through these steps. Some of these steps are kind of jokes because there's not much you do on this step. Like step 1, make sure the coefficient of y double prime is 1. Step 2, another kind of a joke of a step, but the 9-step program sounded better than the 4-step program. Okay, 9 steps sounds like we're getting somewhere. Identify f. Step 3, compute the complementary solution. Step 4, after you compute it, you should be able to identify y1 and y2. Number 3 is where the work is. Number 4 is kind of just pointing things out. Number 5 is compute the Wronskian of y1 and y2. Number 6, there's the recipes that we derived. u1 prime is minus y2f over w, and u2 prime is y1f over w. I wish it was completely symmetric and that negative wasn't there, or there was a negative on there, but it's just the way it goes. It came from Cramer's rule. Number 7, integrate to find u1 and u2, because that's really what we're after, because our trial solution looks like u1 y1 plus u2 y2. And that's step 8, to write that down. And then step 9, well, pretty much you're just putting step 3 and step 8 together, adding them together, and getting a general solution. So that was the derivation of variation of parameters. Of course, we could have drawn this out for more than 15 minutes. We're almost getting to the 16-minute mark for this PowerPoint. We could have gone like half an hour or 45 minutes and gone a little deeper into this, but I think this was already too much for a lot of people. And the rest of this lecture is just going to be me writing out some solutions to some problems and talking us through it. So let's go to problem number 1, which was actually the problem that I had written on the first page. We are going to do variation of parameters and solve this differential equation. So let's go ahead and go through the steps. Step number 1, make sure the coefficient of y double prime is 1. And guess what? It is. Okay, step 2, identify f. There it is. Step 3, compute the complementary solution. How do I compute the complementary solution? I solve the associated homogeneous differential equation, which looks like this. Okay, so let me go ahead and write down my auxiliary equation. R squared minus 2r plus 1 equals 0. This is r minus 1 squared equals 0. So this gives me r equals 1, and also 1, okay? And so my complementary solution, yc, equals c1 e to the x plus, got to put that extra x in this one, c2 x e to the x. And this gives me the complementary solution, which finishes step 3. Step 4 tells me to compute the Wronskian of y1 and y2. Oh, no, sorry about that. Step 4 tells me to identify y1 and y2. So this guy right here is y1. This guy right here is y2. We know that the other part, the trial solution, is going to look like this. It's going to look like u1 y1 plus u2 y2. So the rest of this problem is hunting for u1 and u2. Okay, so step 4 was to identify those guys. There's y1 and y2. Step 5 is to compute the Wronskian. The Wronskian looks like this. I'm going to go ahead and put y1 right here, and y2 right here, x e to the x. Now the Wronskian, I take the derivative below, so the derivative of e to the x is e to the x, and the derivative of this guy right here is a product rule, the derivative of the first times the second, plus the first times the derivative of the second. I'm going to go ahead and take the determinant. The determinant happens to be e to the 2x plus x e to the 2x minus x e to the 2x. So these guys are out of here. And the Wronskian happens to be e to the 2x. So there's the Wronskian. That completes step 5. Remember, there's 9 steps. Step 6 asks us to do those recipes that we learned. So I'm going to go ahead and use another piece of paper here. And so my recipes. So I got to remember these recipes. Here it is. U1 prime, and this is what we spent a lot of that PowerPoint deriving. The U1 prime is negative y2 f over w. So let's go ahead and see what y2 is. It is x e to the x. So this is negative x e to the x. F of x, which you can't see in the picture anymore, it's that guy right there that I identified from step 2, circled up there. I'm going to put that in here, so that's e to the x over x, and then I'm going to divide by the Wronskian. The Wronskian is the thing we just computed, so the Wronskian is e to the 2x. Now I could do a copy dot flip on this, and I'm going to end up getting negative x e to the 2x. This is all over, don't forget that x on the bottom, x e to the 2x. Oh, look at this. This is sweet. This gives me negative 1. As sweet as math can be. Okay, so it's not really literally sweet. Well, maybe it is. There is u1 prime. And so step 6 asks me to find u1 prime and u2 prime. So u2 prime is y1f over the Wronskian. y1, that is right there. That's e to the x. See how we're looking there. Okay. So e to the x. My function was e to the x over x. I'll just go like that on that one. So that's what f is. And then the Wronskian I'm going to put at the bottom, which is e to the 2x. E to the 2x. Of course, this is going to equal the e's to the x's and the e to the 2x. That cancels. I'm going to have 1 over x. And so that gives me u1 prime and u2 prime. Okay, so what am I going to do with u1 prime and u2 prime? Well, that's step 7. Step 7 tells me that I must integrate those. So u1 equals the integral of negative 1 dx. So this is going to give me negative x plus c. Let's go ahead and make the plus c be like in purple. So we're going to say that when you do this process, you do not need to put the plus c. If you leave them in, you'll see that they get absorbed into the C1, C2. So you know what, I'll actually leave them in. I'm going to put a plus c there, you know, maybe I'll put a plus c. I better make this a C3 because I already have a C1 there. But the next time I do one of these problems, I'm not going to write that down. And this might remind you of the method of the integrating factor. The integrating factor, you can let the c equal 0, and we showed you why that was true. u2 is the integral of u2 prime, the integral of 1 over x dx. The integral of 1 over x is the ln absolute value of x plus C4. Okay. And so we'll put that in, but we can let those CI's equal 0. And some of you who still care about this class might want to like go, oh well, why can we just let those equal 0? Just follow this work here. Also notice that right here, my original differential equation, f was e to the x over x. So I'm solving my differential equation not for all real numbers. I have to pick which side of 0 I want to solve it on. Most of the times you want to pick the positive side, especially if you're doing something with time. So if x is positive, then I don't have to write ln absolute value x. I can write this as ln x plus C4. I'm going to keep changing the colors here, plus C4. Okay, so that gives me what I want. That is step 7, which could be the hardest step, you know, depending on what you have to integrate. Step 8 tells me to write out yp. Okay, so let's see here. So remember that yp is u1, y1 plus u2, y2. Let me just write that out here. So yp is u1, y1 plus u2, y2. And so yp is u1, which we found right here, negative x plus C3, and I'm not going to do it in purple this time. I'm just going to remember that. We'll have to show you that those will go away, times y1. Now, y1, hopefully it's still in the picture there. y1 is e to the x. And then we have u2, so that's going to be plus u2, which is ln x plus C4 times y2, which is x e to the x. So let's go ahead and rewrite this. This is y sub p equals negative x e to the x plus C3 e to the x plus, how are we going to write this here? We're going to write it as x e to the x ln x plus C4 x e to the x. Okay, so what I'm claiming now, I want to make sure everything is captured in the picture there. Good. I have my yc here and my yp there. So step 9 says to write out the whole solution. What I'm claiming is that these terms right here can get absorbed into the complementary solution. So, how could I do this? I'm going to go ahead. The wonders of doing your lectures on a piece of paper. I'm doing some paper folding here. We have that right there. I can kind of put a box around this. And so we move this up there. And I'm going to go ahead and do step 9 where I'm writing my final answer. Step 9 looks like this. Y equals, how does this look in the camera? Oh, some shadow there. Okay. So Y equals YC plus YP. So let's just write this down. This is C1 e to the x plus C2 x e to the x minus x e to the x plus C3 e to the x plus x e to the x ln x plus C4 x e to the x. Now I'm claiming, and I'll go ahead and circle these in orange again, that these guys, maybe next time I do the problem, they shouldn't even be there if I went ahead and took my C you know, my constants of integration when I found u1 and u2, took those to be 0. And the rationale behind that is, let's just take a look at those guys. Okay, so let's just circle those guys. Well, notice what happens right here. If you take this one right here and this one right here, I mean, it is c1 plus c3 e to the x. And c1 plus c3 is just another constant. And then the same thing over here. You take these guys right here. I'll put 2 check marks by them. You'll end up getting c2 plus c4 x e to the x. So let's go ahead and just write out the solution. And I'm going to let the c1 plus c3 equal c1. Okay, so c1 e to the x. It's a different kind of c1. And then we have plus c2 x e to the x. Okay, so that right there was the complementary solution. And we just kind of showed that, you know, we don't really need to have those there. And then we have some other stuff right here. We have minus x e to the x plus x e to the x ln x. Okay, so we want to, you know, say, oh, let's box our answer, and we've got a final answer, and it is a legitimate answer, but it is not completely simplified. And this is probably going to upset some people, but let's take a look at these guys right here. Those guys each have an x e to the x in common. So I'm going to factor that out, x e to the x. And when you factor that out, it gives you a c2 minus 1. What is c2 minus 1? This guy right here is a constant, which we're going to call, take a guess, c2. We can call it c5 if that makes you feel more comfortable. So some of our trial solution gets absorbed into the complementary solution. This does not always happen in every problem you do. Sometimes it happens and sometimes it does not. So let's write our final solution to this. So this right here, this green part's just going to become a constant times x e to the x. So y equals c1 e to the x plus c2 x e to the x. And as you can see, this one's not going to get absorbed into anything. I mean, I know that it shares an x e to the x, but then you also have another function of x which cannot get absorbed into a constant. So we have to keep it just like this, x e to the x ln x. It was a second order differential equation that we started off with. We have 2 ci's. There is the general solution. So that is how you do these variation of parameters problems. We kind of slowed down on this one. Where did we slow down? We slowed down when we did this and we put the C3 and C4 there. So how about next time when I find out, you know, when I'm doing this integration here to get U1 and U2, I am not going to put a C3 or C4. I'm just going to let the constants in each of these be 0, and I'll save myself a lot of time. So this one was lengthier than it should be just because we were writing every step and we were doing some things that maybe we can not do next time. Let's go ahead and do another problem. Okay, where is my next problem? Oh yeah, this is gonna, people are gonna like this here. Why? Because it has some trigonometry in it. We have the cosecant x. It's not even one of the main players, sine, cosine, tangent. I know we can write it as you know, in terms of sine, but let's go ahead and do this problem. And we'll do our 9-step program. Maybe you want to pause the video and see if you can do this yourself. Okay, now what we're going to do is step 1, make sure the coefficient in front of the y double prime is 1. Well, it is. We don't have to write that, but I'm just showing you that I just made sure of that. Step 2, identify f. F happens to be that guy right there. Okay, now step 3 is I want to find y sub c, the complementary solution. To find the complementary solution, I'm going to write the associated homogeneous differential equation. It's going to be y double prime plus y equals 0. The auxiliary equation is going to say r squared plus 1 equals 0. I'm going to go ahead and solve for r. What I'm going to get for r is plus or minus I. So y sub p is going to equal, if you like, you could put 0 plus or minus I e to the 0x. So this is going to equal c1 cosine x plus c2 sine x. And this completes step 3 of the 9-step program. We found, the complementary solution, which should not have a yp there. It should have a yc. So we still have this white out here. Cool. And we have yc. Hopefully I didn't say particular solution. But there it is right there. Okay, so we know that we know kind of how our particular solution is going to look. There's our complementary solution. We also, for step 4, want to identify this one and call this one y1, and this guy right here is y2. Now, we don't have to write this down, but we know that our particular solution is going to look like u1 y1 plus u2 y2. And we know what y1 and y2 are. We are going to spend the rest of this problem finding u1 and u2. So, next step. So step 4 was identify y1 and y2. Step 5 is compute the Wronskian. The Wronskian of y1 and y2 looks like this. So you put y1 there and y2 here. And remember the Wronskian, you take the derivative of this and you write it below. So the derivative of the cosine is the negative sine, and the derivative of sine is positive cosine. And now we have a square matrix, so I'm going to take the determinant, which is the cosine squared x minus a negative sine squared x, so it's actually plus sine squared x. And this, hopefully you recognize this cosine squared plus sine squared is 1. So the Wronskian equals 1. That completes step 5. Step 6 is going to be the recipes. And we're going to find u1 prime, u2 prime. So the recipes for u1 prime. So u1 prime is negative y2f over Wronskian. And so negative y2, that's this guy right here, so negative sine x. F is the cosecant. You can look back and see that. The cosecant x. And the Wronskian is 1. Now, look what we have here. We have negative sine x. And if you remember your trig identities, the cosecant can be written in terms of 1 over the sine x. So our u1 prime is actually going to equal negative 1. That's not always going to be the case. I know u1 prime, was that in the last problem? It equaled negative 1. Yeah, I should look at my problems before I do them. That's not always going to happen. So do your homework and you'll see that u1 prime will sometimes equal other things. Most likely. Okay, u2 prime equals y1f over Wronskian. So y1f is, well, y1 is the cosine of x, and f happens to be the cosecant of x, and then we have 1 right there. So what do I have here? I have the cosine x x over the sine x. Now some of you would say, hey, that is the cotangent x. Okay, so great, that's cute. It is what it is. We can write either one of them when we go ahead and do our integration. So this completes step 6, which has to do with the recipes. Step 7, I guess we don't need that Wronskian anymore, says go ahead and integrate this -1. So that's what I'll do. I'll say the integral of -1 dx. That happens to be -x. U2 is going to be the integral of whatever one you want to pick. I'm going to pick the cosine over the sine, and I'm going to eyeball this. So the derivative of the sine is the cosine, so that cosine is going to disappear, and the antiderivative of 1 over u is ln. So I'm going to write this as the ln of the absolute value sine x. And we're not going to put the plus c's because they'll, we saw what happened, that you can take the c to be 0. So let's go back to this problem here, our original problem, and look at the cosecant. The cosecant, if you remember, is the inverse of the sine, and the sine looks like this, etc. And so the cosecant, if we wanted to draw that picture, it has vertical asymptotes everywhere the sine hits the x-axis. Some of you didn't want to see this. So the cosecant looks like that. That. Some of you would go, oh, those look like parabolas. They're not truly parabolas because they don't open up from -infinity to infinity, but it looks like that. And this right here is pi and 0. So when I solve this differential equation, I'm going to choose to solve it on the interval from 0 to pi. Well, 0 to pi happens to be where the sine is positive, and some of you might go, what would happen if I forgot this? It wouldn't be the end of the world. I think I would still give you full credit, but you can drop the absolute values on this and say ln sine x. Okay, and just put it like that. I'm putting the parentheses because it would look too freaky, ln sin x, you'd be like, what is that? So this is the ln of the sine of x. So now it is time to write out the formula here. Our y sub p is going to be u1 y1 plus u2 y2. u1 is -x, and oh yeah, here's y1. y1 is the cosine of x. So let's move this up here. y1 is the cosine of x. And then we have u2, which happens to be the ln sine x. Okay, so that is u2, and then y2 is this guy right here, sine x. So I'll just put him right there. And let's go ahead and write out our final answer now, because we have y sub c, which we did earlier. So that right there was writing out step 8. Step 7 was doing the integration. Fold the paper here. I can fold it correctly. And so there's your complementary solution and your particular solution. Let's write them all out and see if anything absorbs into the complementary solution. I have c1 cosine x plus c2 sine x. Okay, so there's the complementary solution, and then the particular solution is minus x cosine x plus sine x. I'm going to throw some parentheses around there, and then we have the ln of the sine x. And so that's what we have right there. Now you might say, oh, well, this guy right here and this guy, you can factor out a cosine of the ones I'm pointing to. And that is true. You can write them together and factor out a cosine. But inside parentheses, you'll have C1 minus x, which is not to be replaced with a constant because of that x. So this guy cannot be absorbed into that. This answer is the general solution. And so that happens to be the method of the variation of parameters, which took us about 28 minutes. So at this point, we have finished chapter 8. And I had another problem. This is extra. So, you know, like right now, most of you might turn off this video. This is just for the math majors and the extra motivated students. And so I'm going to go ahead and show you this one. You're not going to get anything like on your homework. So, you know, for most of you, turn off. So most of you turn off the video. Okay, because this is only going to harm some of you. And for the math majors, and you know, maybe you're a math major, you turn off the video as well. I don't know. What is kind of weird about this one is the fact that it does not have constant coefficients. So look at this differential equation. It has an x squared there, and it has a negative 4x, and we have a plus 6y. So this thing is, it doesn't, you know, we're a little upset because there's not constant coefficients, and we have not been trained how to do this. But the first thing you want to do is make sure the coefficient of y double prime is a 1. I'm going to have to divide everything by x squared. And when I do that, I end up getting y double prime minus 4 over x y prime, and then I have plus 6 over x squared y. This equals 1 over x cubed. Okay, so that's what happens when I divide everything in that equation by an x squared. Step 2 is identify f. There it is. Step 3 is to find the complementary solution. Now, guess what? We gave it to you because we have not been trained how to solve these differential equations when the coefficients are not constants. Okay, so wow, we don't know how to do this, and you can learn how to do this kind of on your own, or just wait until you have to take another differential equations class. This is called the Cauchy-Euler equation. And so that's what we're given, but given this, we can actually finish this problem. So this is step 3, which was kind of, you know, I gave it to you. Step 4 is to identify y1 and y2. y1, we're going to call it that one right there, and y2 is that one. Okay, step 5 is to compute the Wronskian. The Wronskian, I'm going to go x squared, x cubed, and take some derivatives here, 3x squared, and then take the determinant. We take the determinant, I end up getting 3x to the 4th minus 2x to the 4th, which is x to the 4th. That's the Wronskian. u1 prime, so now I'm doing step 6. This is the recipe. Negative y2f over Wronskian. Negative y2, that is negative x cubed, and then f happens to be 1 over x cubed, 1 over x cubed, and then the Wronskian is x to the 4th, so this is multiplied by 1 over x to the 4th. So this gives me negative 1 over x to the 4th. And if you're going to try to integrate that, it would be negative x to the negative 4 power. Y, no, that's not y. I've got to go learn my alphabet again. u2 prime is y1 f over Wronskian. y1 is x squared, and then we have our function f, which is 1 over x cubed, and then the Wronskian is x to the fourth, so I'm going to go times 1 over x to the fourth. And so this gives me 1 over x to the fifth, which is really x to the negative 5. I'm going to move over here and do some integration here. So u1 is the integral of this, which is really going to be, we add 1 to that, remember, and so that gives us a negative 3, and we put it on the bottom, and so when all the dust is settled, we end up getting 1 over 3x to the third. And then the same thing with this. When we integrate this, we add 1 to that. This is the power rule for antiderivative, so this is negative 4, and we put a negative 4 on the bottom. So when all the dust is settled on this one, we end up getting negative 1 over 4x to the fourth. So the yp actually equals, let's figure this out, it is u1 y1 plus u2 y2. u1 is 1 over 3x cubed times y1, which is x squared, plus we have u2, which is negative 1 over 4x to the fourth, times y2, which is x cubed. So this gives me 1 over 3x, and then this is minus 1 over 4x, get a common denominator of 12x, so this will give me 4, 4, 4, and then minus 3, so this, when you simplify this, gives you 1 over 12x. So there is the particular solution. So step 7 was here integrating, step 8 was writing the particular solution, and then step 9 is putting them all together, which then gives you your general solution. Y equals c1 x squared plus c2 x cubed plus 1 over 12x. So why did I do this problem? To illustrate the fact that the method of annihilators works pretty good on a lot of the problems that we had to do, like with springs and with circuits. But this just shows you that the variation of parameters technique, when you're trying to find a trial solution, works for things that do not have constant coefficients, and it works. But you have to get this first, and that's another class, a higher class. And then once you get this, you could use what we've just learned in the other two problems and crank out the general solution. Have a good day.